Hi everyone, I'm Rosa de Finis from Polytechnic University of Bari. This work investigates the possibility to evaluate the crack deposition, the crack growth rate, and the stress intensity factor in severely notched samples in order to derive the Paris law by starting from the temperature distribution measured by means of an infrared camera with high geometrical resolution. Firstly, let me to give you an overview of this presentation. The state-of-the-art, referring to the role of thermoelastic stress analysis for fracture mechanics assessment, will be clarified. The aims of the present work will be shown, and also theory referring to the thermoelastic stress analysis temperature formulations combined with Westergard and Williams solution, experimental setup, methods, results, and conclusions will be also presented. Thermoelastic phase shift has been widely used for the fatigue crack growth evaluation. It represents the phase angle between thermoelastic and loading signal. In general, phase angle remains locally constant in presence of linear elastic behavior and steady-state condition. It can change due to plastic behavior and high stress gradients, leading to heat conduction and loss of adiabatic condition. In effect, in proximity of the crack tip, there is a positive increment of the phase value that indicates a loss of adiabatic condition due to plasticity and high stress gradients. Then the phase change from positive to negative values, indicating reverse plasticity, and then it returns to zero. This point can be empirically considered as the crack tip estimation, while in this area adiabatic conditions are achieved. As for the stress intensity factor, it can be experimentally assessed by using thermoelastic stress analysis. In this way, Stanley presented a procedure based on Westergard solution for the elastic plane stress condition, where the stress intensity factor can be obtained by relating the first stress invariant and the crack tip position. The main drawback of the approach regards the neglection of the T-stress term in Westergard equation. Instead of using a linear interpolation method, it is possible to use the overdeterministic least square based fitting method combined with Williams or Westergard solution to obtain a more accurate estimation of the stress intensity factor. In effect, in the work of Pitaresi, the effect of the T-stress was considered together with the influence of the number of the terms in Williams solution. The aims of the present work focused on single-edge notch and tension samples are to compare the crack deposition, the crack growth rate, and stress intensity factor obtained via different thermoelastic stress analysis based methods, and to discuss the capability of different methods to estimate the Paris law. Thermoelastic effect relates the temperature change with the change in the sum of principal stresses of an isotropic material in linear elastic and adiabatic condition. The thermoelastic equation was derived imposing the conservative laws which govern the mechanics of small quasi-static deformation and the second law of thermodynamics for a reversible process. For an isotropic material without any internal source, the temperature variations can be described by taking into account constitutive law, Lamin constant, coefficient of thermal expansion, and neglecting high-order terms, writing all clearly in function of principal stress and first stress invariant. For a one-dimensional stress state where the stress changes over the time with the sinusoidal waveform, it is possible to observe the dependence from mean stress and the second-order terms that depend on the square of stress amplitude. By starting from the previous equation where A and B material constant have been included together with principal stress, and also by expressing principal stress as a sinusoidal function and expressing all in function of the loading ratio, it is possible to write this temperature variation through time as composed by two parts, two periodic function, two parts, and after after time integrating, it is possible to obtain the general expression of the thermoelastic signal in proximity of a crack under the hypothesis of small temperature variation if compared to environment temperature. And in present work, we focus on this first component, in particular on its amplitude, to express the temperature variation. And then by combining Westergard solution with the T-stress with the general expression of the thermoelastic signal previously assessed and focusing on its first component, and by posing the B constant equal to 0, it is possible to obtain the classical solution used for relating the thermoelastic signal and the stress intensity factor. On the other side, in order to use Williams solution truncated to the third term and combined it with the general expression of the thermoelastic signal previously assessed, the same first component we used, and by posing the material constant B equal to 0, it is possible to obtain the classical solution used for relating thermoelastic signal and stress intensity factor using, in this case, the Williams formulation truncating to the third term. In this work, 2 single-edge notch tension samples have been addressed to load-controlled crack propagation fatigue test under fully reversed load. The load was applied at a loading frame, a shank hydropulse loading frame with 100 kN of capacity. The tests were assisted by a cooled infrared camera with a noise equivalent temperature difference less than 25 millikelvin, and the sequences were acquired at 200 Hz. The tests were also assisted with a Dino-like digital microscope positioned specularly to the infrared detector, and in this table it is possible to find the loading parameters as well as the crack growth rate measured and the stress intensity factor obtained via numerical analysis. And now let's go into methods and data analysis. In particular, the temperature data processing involved a signal reconstruction algorithm based on least square method that provided the composition of the thermal signal in its component. In particular, in this work, we focused on the first component, which amplitude is the thermoelastic amplitude, and the phase shift represent the thermoelastic phase shift discussed before. Referring to the second component, it is related to the double reverse plasticity and in general to intrinsic dissipations, and it is also possible to use the phase shift of the second harmonics to estimate the crack tip in the same way as the thermoelastic phase shift. And now, just to give you an overview of the carried out analysis, we determined the crack tip and then the crack growth rate by using the point inversion of the thermoelastic phase and a second order phase shift. We determined the crack tip via also overdeterministic method combined with Williams, Westergard plus T-stress and Westergard. And also we compared this crack tip and crack growth rate with the one obtained by using optical microscope. As for stress intensity factor, the stress intensity factor evaluated via Stanley chain method and via overdeterministic methods has been compared to the one obtained by numerical analysis performed by using finite element methods. Notch stress intensity factor was estimated from finite element analysis carried out by using a mesh pattern with a constant element size. In particular, it was adopted the peak stress method that allows to evaluate the elastic peak stress at the V-notch tip via numerical analysis, with the advantage to use a rather coarse mesh. The analysis requires the evaluation of a virtual V-notch tip radius that can be determined theoretically for a given geometry as discussed in the work of Professor Meneghetti. Once it was determined, the expression can be applied to the specific notch geometry, notch depth, and opening angles. In particular, in this case, the opening angle was of the V-notch-shaped notch was 45 degrees, and the carried out analysis on ANSYS used a simple enhanced strain method. Finally, possible by simply determining the singular linear elastic peak stress, it is possible to obtain the stress intensity factor. As for the crack tip evaluation using thermoelastic phase shift and second order phase shift, firstly it is important to determine the maximum in the amplitude map, and the time the maximum has been assessed, the profile passing through this point on phases map is plotted, and on that profile it has been evaluated the point of inversion. That point of inversion represents on phase 1 and on phase 2 the estimation of the crack tip. Now the workflow of the analysis to obtain crack tip and stress intensity factor via overdeterministic methods. In particular, the thermoelastic phase maps are used to assess the crack tip position initial value, while the thermoelastic temperature maps are used combined with the information provided by the thermoelastic phase to set the semi-annular mesh of the selected data point in the elastic zone, and moreover, for the considered thermoelastic model, an overdeterministic system of equation was written by substituting each value of the thermoelastic signal of the selected data points together with the calibration parameters together with the loading condition in the temperature formulation we saw before, where the unknown of this system are the stress intensity factor and the T-stress. As for the crack tip assessment, we have different methods. From thermoelastic maps for sample 1 at difference crack length, it results a maximum difference of 0.4 millimeters when estimating the crack tip via TSA based methods. And this is there is a good agreement between the crack tip found by using TSA based methods and the reference, the optical microscope. And above all the methods allow to estimate the crack tip position in a very good confidence. As previously confirmed by the crack tip position detected, a good agreement between the TSA-based methods is observed in comparison with optical microscope detecting the crack lengths. In particular, a slight underestimation seems to be present for all the methods except for overdeterministic method combined with the Williams solution. As for the crack growth rate compared to the stress intensity factor from finite element method, a slight dispersion with respect to the crack growth rate obtained from the optical microscope estimation is observed. The same conclusion can be drawn for these second samples referring to the crack tip assessment. In effect, from the thermoelastic map at different crack lengths, it's possible to see that it results a maximum difference of 0.3 millimeters when estimating the crack tip. So that even in this case, it's possible to say that there is a good agreement between the crack tips found by TSA-based methods and the reference of the optical microscope. As for the crack length, for this sample 2, it is possible to find a very good agreement with the data, the crack length provided by optical microscope. And the crack length provided by optical microscope and the different methods allows to obtain the crack growth rate. And when comparing the crack growth rate to the stress intensity factor obtained via finite element methods, it is possible to observe a slight for a specific value of stress intensity factor, a slight dispersion and a general underestimation and overestimation for some point. And now all the data provided by thermoelastic stress analysis based methods in terms of stress intensity factor and crack growth rate evaluated, and reference data, those obtained by using FEM and optical microscope, have been put in the same graph, and it is possible to observe that the results show that the major part of the point lie in the 95% confidence bounds associated with the fitting of the reference data series. And in particular, from Stanley-Chan method, point orange and gray, to evaluate the stress intensity factor combined with the crack growth rate obtained by using the point inversion of thermoelastic phase shift and second order phase shift, provide results in good agreement with the reference. The overdeterministic methods combined with Westergard solution provide scattered data that belong to the confidence interval just for some point, while more robust Williams solution data are noisier, point green and cyano, and sometimes out of the confidence bound due to an underestimation of the stress intensity factor. This data scatter may be due to the influence of the half cycle in compression, where the crack closure effect could influence negatively the less square fitting, so that further work is required to understand better such an influence on overdeterministic method. In this work, crack tip position and stress intensity factor evaluated by using thermoelastic stress analysis based methods have been compared to the stress intensity factor obtained via numerical analysis and crack growth rate obtained by using the data from optical microscope. And this way it is possible to conclude that for single edge notch tension samples there is a good agreement in detecting crack tip by using optical microscope and TSA based methods, and as for stress intensity factor, the results show the Stanley-Chan method, that is less robust than the overdeterministic method, provide close to FEM values, and overdeterministic methods seem in this preliminary analysis to underestimate the stress intensity factor, but in this way further analyses are required to study such the phenomenon. And thank you for your kind attention.